Next theorem is Wolstenholme's theorem. The statement is for any prime p greater than or equal to 5, we have summation k equal to 1 to p minus 1, p minus 1 factorial upon k is congruent to 0 mod p square. So we take g of x equal to, let the polynomial g of x equal to x minus 1 into x minus 2 into etc. x minus p minus 1. On simplification, we will get x power p minus 1 minus some s1 x power p minus 2 plus etc. minus sp minus 2 into p plus sp minus 1, where sr is nothing but the sum of product of 1, 2, etc. p minus 1 taken r at a time. For example, sp minus 1 is nothing but 1 into last term, that is the constant term, 1 into 2 into 3 into etc. p minus 1, which is equal to p minus 1 factorial, and sp minus 2 is sum of product of 1 into 2 into etc. 1, 2, 3 etc. p minus 1 taken p minus 1 times at a time, that is it is 1 into 2 into etc. p minus 1 plus 1 into, sorry, it's p minus 2, then 1 into 2 into etc. P minus 3 into p minus 1 plus 2 into 3 into etc. p minus 1, like this, that is we will get, which is equal to summation k equal to 1 to p minus 1 factorial divided by k. This is sp minus 2. Actually, we have to prove that this sp minus 2 is congruent to 0 mod p square. So we have to prove that p square divide sp minus 2. This is the statement actually. Okay. Now we consider we have g of x equal to x power p minus 1 in minus s1 x power p minus 2 plus etc. minus sp minus 2 power p plus sp minus 1. Therefore, we will get g of p is nothing but p power p minus 1 minus s1 p power p minus 2 plus s2 p power p minus 3 minus etc. minus sp minus 2 times p plus sp minus 1. And by a known theorem, we can see that x minus 1 into x minus 2, if you take the polynomial x minus f of x equal to x minus 1 into x minus 2 into etc. x minus p minus 1 minus p x power p minus 1 plus 1. If you take f of x like this, then every coefficient of f of x is divisible by p. We know this theorem, every coefficient of f of x is divisible by p. In particular, we can say that this is g of x. Every coefficient of g of x is also divisible by p, or we can say that p divides s1, p divides s2, etc. p divides sp minus 1, p minus 1, p divides sp minus 2. Okay, now this is g of p, and we will take these two terms on the left side. We will get g of p plus sp minus 2 into p minus sp minus 1 is nothing but p power p minus 1 minus s1 p power p minus 2 plus etc. plus sp minus 3 into p square. Okay, then we can say that every terms of the right hand side is divisible by p cube, that is p cube divide right hand side, because each term contains p cube, p power p minus 1 contain p cube, p power p minus 2 contain p cube, etc. Here already p square exists and sp minus 3 contain a term in p. Therefore, we can say that p cube divide RHS, therefore p cube divide LHS. That is p cube divide sp minus 2 into P minus SP minus 1 plus G of P. Now let's check what is G of P. G of P is nothing but G of X is nothing but X minus 1 into X minus 2 into etc. X minus P minus 1. This is G of X. Therefore, we put P instead of X. Therefore, we'll get P minus 1 into P minus 2 into etc. P minus 1, which is nothing but here 1 into 2 into etc. into P minus 2 into P minus 1, which is nothing but P minus 1 factorial. G of P is P minus 1 factorial, and we already see that SP minus 1 is also P minus 1 factorial. SP minus 1 is P minus 1 factorial, the last constant term. Therefore, we can cancel the two terms. Therefore, we will get P square divide, P cube divide P into SP minus 2, or we can say that P square divide SP minus 2. Hence the proof. That is, in the statement we have to show that SP minus 2, that is summation k equal to 1 to P minus 1 factorial by k is divisible by P square. Therefore, here we get P square divide SP minus 2, hence the proof. Move on to our next theorem, that is Chinese remainder theorem. The statement is, assume m1, m2, etc. mr are positive integers relatively prime in pairs. That is, if you take any two real positive integers mi and mj, they are relatively prime in pairs. So their greatest common divisor is actually 1 for I not equal to k, and like b1, b2, etc. br are arbitrary integers, then the system of congruence x congruent to b1 mod m1, x congruent to b2 mod m2, etc. x congruent to br mod mr has exactly one solution modulo the product. We have to prove this. So, given that GCD of mi and mj is 1 for all I not equal to j, they are relatively prime, and put capital M is equal to the product m1, m2, etc. mr, and capital Mi is equal to capital M divided by Mi. That is, we will get m1, m2, etc. mi minus 1, mi plus 1, etc. mr. That is, each term mi does not contain the term small mi, or we can say that GCD of mi and capital Mi is 1, and all other terms small mj divide capital Mi. Only the small mi does not divide capital Mi, all other terms divides capital Mi. Since GCD of mi is equal to 1, we can use a non-theorem, that is mix congruent to 1 mod m has a unique solution. That is, if GCD of A and M is 1, then the congruence X congruent to B mod M has a unique solution. We use that theorem. Therefore, we will get MIX congruent to 1 mod M has a unique solution. Let it be Mi dash. The unique solution is Mi dash. Therefore, Mi dash also satisfies the congruence, that is Mi dash congruent to 1 modulo M, congruent to 1 modulo M. Or we can say that Bi Mi dash congruent to Bi mod Mi. We multiply Bi both sides. We can say that Bi Mi dash congruent to Bi mod Mi. Equation number 1. Now we put x is equal to b1 m1 dash plus b2 m2 m2 dash plus etc. br mr dash. Then we have b1 m1 dash plus etc. bi minus 1 mi minus 1 capital M I minus 1 dash plus B I plus 1 M I plus 1 Mi plus 1 dash plus etc. plus BR mr dash is congruent to 0 mod mi, small mi. This is because we already said that each small mi is divide capital M1, mi divides capital M2, mi divides mi minus 1, but mi does not divide capital Mi. But mi divides all other mj's, therefore mi divide mi plus 1, mi divide I plus 2, mi divide mr. Therefore mi must divide this combination also. This is equation number 2. Then we add equation number 1 and 2. Then we will get left side as x, because the term is bi, mi dash is added here. Therefore we will get right side as x congruent to right side is bi. Here right side is 0 and this is bi. Therefore we will get x congruent to bi mod mi for all I. This is satisfied by for all I, or we can say that x congruent to bi mod the product m1, m2, etc. mr. That is because x congruent to bi mod m1, x congruent to b2 mod m2, etc. x congruent to br mod mr. Therefore x congruent to some br mod okay. Then x congruent to bi mod m for all m I equal to 1 to etc. R, therefore x congruent to bi mod capital M, the product capital M. This is the unique solution. This is the proof of Chinese remainder theorem. Then as an application, let's see the problem related to Chinese remainder theorem. Find the x which satisfies simultaneously the system of congruence x congruent to 2 mod 3, x congruent to 3 mod 4 and x congruent to 4 mod 5. This is actually the problem. So we take b1 equal to 2, b2 equal to 3, b3 equal to 4 and small m1 equal to 3, m2 equal to 4, m3 equal to 5. That implies capital M is nothing but the product m1, m2, m3, that is 3 into 4 into 5, which is equal to 60. Therefore capital M1 is 60 divided by 3, that is equal to 20. Capital M2 is 60 divided by 3 into 5, 15, which is equal to 16 divided by 4, which is equal to 15, and the capital M3 is 60 divided by 5, which is equal to 12. Now consider the congruence. Here each mi, m1, m1, GCD of m1, m1 is 1, m2, m2 is 1 and m3, m3 is 1. So consider the congruence. First congruence is 20x congruent to 1 mod 3. This congruence has a unique solution and it be x equal to, or mi dash, we take the solution as m1 dash equal to 2. Okay. Then next consider the congruence 15x congruent to 1 mod 4. Then we will get the solution m2 dash as 3. Then third one is 12x congruent to 1 mod 5. Therefore the unique solution m3 dash is nothing but 3. Therefore we can take the solution x as b1 m1 m1 dash plus b2 m2 m2 dash plus b3 m3 m3 dash. Now which is that implies x equal to 2 into 20 into 2 plus 3 into 15 into 3 plus 4 into 12 into 3, which is equal to 359. Therefore, we can say that all the solution is of the form x congruent to 359 mod 60, or we can say that x congruent to 59 mod 60. This is the system of equation, the solution which satisfies the system of equation x congruent to 2 mod 3, x congruent to 3 mod 4 and x congruent to 4 mod 5. Then move on to next problem. Prove that n raised to 13 is congruent to n mod 1367. So first we factorize 1367. 1367 can be factorized and write in the form 3 into 5 into 7 into 13. Now we show that 3 divides n raised to 13 minus n, 5 divides n raised to 13 minus n, 7 divides n raised to 13 minus n, and finally 13 divides n raised to 13 minus n. Then we can say that their product also divides n raised to 13 minus n, that is 1365 is divisible by divides n raised to 13 minus n. So we start with the 3. If 3 does not divide n, we can use Euler-Fermat's theorem that 3 raised to, if 3 does not divide, or GCD of 3n is 1, we can say that n raised to 5 of 3 is congruent to 1 mod 3. That implies n raised to 2 is congruent to 1 mod 3. That implies n square whole raised to 6 is also congruent to 1 mod 3. Or we can say that n raised to 12 is congruent to 1 mod 3. That implies n raised to 13 is congruent to n mod 3. That implies 3 divides n raised to 13 minus n. Okay, if GCD of 3 and n is 1, or 3 does not divide n, in that case we can say that 3 divides n raised to 13 minus n. If 3 divides n, then we can say that 3 also divides its combination n into n raised to 12 minus 1, or we can say that 3 divides n raised to 13 minus n. In both cases we can say that 3 divides n raised to 13 minus n. So we move on to next value, that is 5. If 5 does not divide n, we can use Euler-Fermat's theorem, that is GCD of 5 and n. 5 and n is 1, that implies n raised to 5 of 5 is congruent to 1 mod 5, or we can say that n raised to 4 congruent to 1 mod 5, or we can say that n raised to 4 whole cube congruent to 1 mod 5, that is n raised to 12 congruent to 1 mod 5, that implies n raised to 13 congruent to n mod 5. Or we can say that 5 divides n raised to 13 minus n. If 5 divides n, then 5 also divides the same way. We can say that 5 divides its combination n into n raised to 13 minus n raised to 12 minus 1. Therefore 5 divides n raised to 13 minus n. In same way we can say that 7 also divides n raised to 13 minus n, and 13 also divides n raised to 13 minus 1. Therefore its combination also divides n raised to 13 minus n. Hence we can say that n raised to 13 minus n is divisible by 1365, or n raised to 13 minus n is congruent to 0 mod 1365, or we can say that n raised to 13 is congruent to n mod 1365.